Today what we will be learning about is what is a derivative? A very important question when you start off calculus. In fact, to reach the calculus of derivative, we shall be looking at the two interpretations of it. The two major interpretations that I feel are very important to be understood when we are talking about a derivative. Now, which is, of course, one is a geometric interpretation, which actually makes us see what exactly does a function or derivative of a function looks like. And second, of course, being the importance or usability of it, which is a very subjective matter. Derivatives are used in various fields. Actually, it is used in economics and engineering. For a very small example, let's look at velocity or speed. It is supposed to be a derivative, right? So now let us first of all concentrate on what do we mean by the geometric interpretation of a derivative. So geometry around a derivative, okay. So here I have made for you a simple diagram, okay, in case it is not looking that simple. It's a very simple diagram which is showing us a function, okay. What function am I talking about? Let me just color it. Let me just color it yellow. This function f, okay, this function f, okay, this function f is a function of x, so fx, okay, this function f, and let us take one point P, let us take a point P, okay, and Q. Okay, and in case you join PQ, there is a line which I call LXY. Okay, there is a line which I call LXY. LXY. Okay, now this point P essentially, this point P, what do you see here? This point P essentially associates x0 and y0. So this point P is essentially x0, comma y0. So x0 and fx0, which equals to y0. Okay, and this Q is a point, okay, where x is a little far from x0, okay, so I am quoting it as x0 plus h, okay. Q is a point, okay, let me just write it here for you. Q is a point which has x-axis value as x0 plus h and y-axis value as f of x0 plus h, okay. So Q consists of these 2 points, okay. Now moving down, let me see. So we have a function out here, we have a point P out here. Let us find a tangent line to y equals to fx at P. So our aim is to find a tangent line. Okay, let me just draw it. Let me just draw this tangent line. Okay, there is my pen, and that's how this line will look like. Okay, so our aim is to find out this tangent line out here, okay. So let us see how we can do it. Now, let us first of all find out the equation of the tangent at P equals to x0, y0. What is the equation of the tangent? The equation of a tangent is, as given to us here, it is y minus y0 equals to m x minus x0. What is this m? This m is the slope of this curve, slope of this line. So y minus y0 equals to m x minus x0, okay. So there are two unknowns as you can see out here. And what are they? Y naught. Y naught, we do not know Y naught. Y naught is a function of X naught. So Y naught equals to Fx naught is something that we should be finding. And the second unknown is essentially, the second unknown is M, the slope. We do not know the slope. So the slope at X naught is an unknown to us. So we need to know the slope, okay, to get our equation. So we define f dash x naught. So what is f dash x naught? F dash x naught essentially is the derivative of f. The derivative of f at x equals to x naught. It is the slope of the tangent line to y equals to fx at x equals to x naught, or p. Okay. So the slope of this line is the derivative. Now, how do we reach to the slope of this line is the question. So now we have a definition for f dash x naught, or the slope. Now, how do we figure out which line is the tangent? Now, that's the most important part. Now, my question to you is, how do you differ this line PQ from the tangent line LT? So LXY and LT. How do you differ LXY and LT? LT is the tangent line, so LT. Okay, how do you differ these two lines? Now, what is happening is that LXY, if you notice, LXY is cutting through the function. It's cutting through the function, in fact, at 2 points, okay? It's cutting through the function. In case we make LXY start moving and moving so that it's just touching at point P. So that it's just touching at point P, what will happen? LXY will turn into the tangent line, okay? So that is what is our aim. So what is our aim? Our aim is we will look at the secant line through PQ, which I have quoted as LXY. Can PQ be a tangent? Yes, PQB can be a tangent. I just told you how it can be a tangent. To be a tangent, is it enough to cut the graph once? No. The tangent is just supposed to touch the curve at one point and not cut it, okay? And not cut is a very important word out here. And not cut. The secant PQ can turn into a tangent at P as Q goes near P. So what has to happen? Q has to go near P, where P is your fixed point at the point where I want to locate a tangent. The point where I want to locate a tangent, okay? So let me just go how we can do it. Let me just see how we can do it. So secant to a tangent, okay? From secant to tangent. So how exactly we will be moving there? So derivation of the formula of a derivative, okay? So what have we seen in the previous figure? Okay, we've been looking at a figure where we had a curve, okay, fx, a curve, and 2 points P and Q. I am only bothered about the points P and Q because what is my aim? My aim is that Q should turn into P, okay? Q should move like that it comes to P, okay? So now, we need to know these 2 points. We need to know these 2 points. The 2 points out here. So, x naught is where P is. X naught is where P is. X naught is where P is, okay? And x naught plus h is where? Q is. So H is essentially the change in X. H is essentially the change in X. Okay. And what will be the change in F? In case you have a change in X, there will be some change in F also, because F is nothing but it's a function of X. Okay. So let us first of all find out the slope of this line PQ. Now the slope of this line PQ essentially is nothing else but the ratio of the change in F to change in X. That's what is a slope. The change in the function with respect to the change in the X, the value of input. So slope of a tangent will be the same as change in X tends to 0, right? Because what is happening for P to become Q, for Q to come to P, the change in X has to be nearly 0. The change in X has to be nearly 0 for this point to move like this and come here. Okay? On the curve. Of course, I haven't drawn the curve here. So that will be the slope of the tangent, right? That will be the slope of the tangent. So we need to find out. So M, which is the slope of the tangent, slope of the tangent, is nothing but change in F upon change in X as this change in X goes to 0. Okay. Change in F is essentially your change in F from P to Q, right? So that will be P is the point from P to Q. What is the change? The difference between the Y value here and the Y value here. So that will be as given here, Fx naught plus change in X minus Fx naught. That will be the complete change in F, right? So M essentially is nothing else but the slope of the tangent, which is limit as change in X goes to 0. Okay. Q turns into P, and instead of cutting as a secant, cutting on 2 points, it will just touch the curve at P. So Fx naught plus change in X upon minus Fx naught upon change in X would essentially be the slope of the tangent. And this is something that we call the difference quotient. Okay, it's in the quotient form. So the difference quotient. Okay, so the difference quotient is this portion. So as the limit of the denominator going to 0, difference quotient will give us the slope of the tangent. And this is what is the first principles formula for finding out derivative also. We'll be looking at certain examples of it in the next videos.